Left, right, right, back, dance.
哦，它有个 return true。哦，我这里是加了一个这个助理器的。这样
你让人不写。
我已经老东西了。等于是你在这里边会一直循环，然后你按键它就不循环，然后如果你这里面不循环的，其实它会变成后期的一个部分。
凑近点，因为他的耳朵，你看，他耳朵动起来了。
Following the demonstration of our project's outcome videos, I'm pleased to present our group project on the module SAP with regard to the selected robot Mirror E. With growing aging populations, especially in urban areas, loneliness has emerged as a critical health issue, contributing significantly to coronary heart disease, stroke, and dementia. So to tackle this challenge, we developed a companion robot based on Mirror E, specifically designed for elderly people, isolated patients, and individuals with disabilities who lack access to traditional companionship or pets. Our robot directly contributes to achieving the UN Sustainable Development Goals for good health and well-being, which is the Goal 3, and industry innovation and infrastructure, which is Goal 9. Our key objectives include enhancing user interaction through gesture, touch, speech recognition, ensuring emotional responsiveness, and interactive feedback. Furthermore, robust obstacle detection is implemented to prevent collisions, ensuring user safety during interactions. And to enrich our emotional connectivity, the robot also simulates emotional states through adaptive lighting responses.
Okay, the first part is the mirror system structure. The system consists around three core components: perception inputs, communication interface, and motion interface. Perception inputs serve as the system's sensory gateway. We receive data from the communication interface to determine specific motion commands. The communication interface plays an important role in the system's operation. It subscribes to those topics to gather messages from various sensors and publish its motion control signals to the corresponding sensors to make sure data exchange and command execution. Finally, the motion interface provides a wide range of control functions designed to interact with users. It dynamically switches between different control states based on the received input parameters. These functions contain that span, wheel move, eye, ear, tail control, and something like that. So this structured approach enables flexible control of the robot's actions, making it capable of responding effectively to various inputs and commands. Then it is certain period control algorithm. Since the mirror control method requires continuous control signals transmission, implementing actions that trigger only for a specific duration requires a delicate algorithm. As you can see in the diagram, the process operates within a continuous loop. During each run, the system monitors sensor inputs such as touch, audio, and camera. When a specific sensor flag is detected and matches the predefined condition, the motion flag is set to true. Once triggered, the motion time is initialized to 0, and the loop begins. The run duration is defined by a parameter called duration, during which the corresponding actuators performs the intended action continuously. Once the loop finishes, the system stops action, resets the motion time to 0, and sets the motion flag to false. And then the system will wait for the next valid trigger to begin a new run. So this algorithm ensures that each action is performed accurately and only for the intended duration.
Regarding the visual interactive module, our visual interaction module employs media pipe and advanced hand key point detection framework, and also it is combined with a lightweight multi-layer perception, classifier. MediaPipe captures precise hand landmarks from real-time video streams, while the MLP model processes these landmarks into normalized coordinate vectors for accurate gesture classification. This integrated approach significantly enhances our robot's responsiveness, enabling immediate, intuitive, and engaging interactions. Overall, our approach promises a comprehensive and emotionally meaningful companionship experience for those needed most.
Now, let's take a look at the embedded and actual performance of vision-based robot-control interactions. As shown in the figure on the right, our system continuously captures and processes camera image data, converting these images into a format suitable for gesture recognition. The system utilizes our previously illustrated gesture detection model to recognize specific human gestures. Once a gesture is detected, corresponding control flags are activated. In the demonstration here, notice how the robot actually interprets the gesture and immediately responds by moving forward, backing up, or spinning around in response to the gesture's command.
Hello everyone, let's focus on safety obstacles avoiding system of our mirror robots. First, about methodology, I encapsulated the sonar sensor and the cleave sensor to get the data for the latter logic. The sonar sensor measures the distance to obstacles directly ahead of mirror, while the cleave sensors on both sides detect the height differences to prevent the robot from falling off edges. We developed an obstacle avoidance logic that operates continuously in the main loop of the program, which is shown in the flowchart. The logic prioritizes safety by checking cleave sensors first, then the sonar distance. Depending on the inputs and the condition function, the system triggers 4 states: inverse motion, left turn, right turn, and U-turn. These states are controlled using flags and are checked and executed continuously. Because the program of a project is highly modular, the obstacle avoidance logic is seamlessly integrated with other modules. For instance, as for the motion controlling module completed by Bottom, when an obstacle is detected, our system triggers a corresponding turning action. Furthermore, as shown in the early video, our obstacles avoiding system works concurrently with the robot's touching and audio feedback mechanisms, enhancing its interaction capabilities. For summary of this part, it has demonstrated a reliable safe system. During testing, Miro was able to detect cliffs and obstacles effectively, respond with appropriate turning actions, and avoid potentially dangerous sceneries.
This part is touch and emotion. The first one here is the touch perception algorithm. As you can see in the touch workflow, touch interaction mechanism allows that the mirror robot process touch inputs from sensors to generate emotional feedback and corresponding behaviors. It uses that body touch flag and head touch flag to trigger specific actions. You can see that in GIF, which shows that the touch cases, it is always equal to 0 when no touch is triggered. Body touch flag detection determines the span direction based on the threshold values. When it's larger than 1000, it will be turn left, otherwise it will be turn right. And then it also activates the elimination, and the other motions are omitted. And then a head touch flag activates behavioral response such as a shake heads, tail control, and ear control. Okay, the next part is the emotion perception algorithm. You can see the emotion workflow. It shows that the emotion module enables a mirror robot to produce various sounds by adjusting violence, arousal, sound level, and wakefulness. By modulating these parameters, mirror generates sounds that reflect different emotion states, effectively show state changes in its mode perception.
This part is speech recognition part. The main goal of this part is to enable mirror to behave like a real pet, capable of understanding simple voice commands and responding with appropriate physical actions. The system uses offline speech recognition model, which allows speech to text conversion without requiring an internet connection. Its fundamental process can be broken down into several steps. First, the microphone captures the user's voice and converts it into standard audio data. Then, the system extracts features from audio use MFCC algorithm, which mimics the way humans perceive sound. These features are then passed into a chain model, usually a deep neural network, which predicts the likely speech units for each audio frame. Finally, Vosk applied a language module and decoder to assemble these units into the most probable words and sentences, producing structured text output. A teammate bottom and when map the keyword to behavior functions. For example, when the user say hello, mirror notes in response. When the hair move, it move forward. The full process works as follows. The microphone captures live audio, sends it into the voice model for transcription. Then the resulting text is checked against a list of predefined keywords. If a match is found, the co-response loss control interface is triggered to make mirror perform the matching action. This part of the system is built on loss framework, taking full advantages of its modular communication structure, which makes the system logic clear and easy to extend.
The results from deployments revealed robust performance in interactive functionalities at the same level of simulations. The obstacle detection module managed real-time avoidance of environmental hazards. Gesture recognition reached an average accuracy of 80%. The audio interaction module employing speech recognition accurately interpreted user commands. And additionally, the tactile interaction module successfully differed from and responded to varying degrees of user tactile interaction, resulting in appropriate emotional performance.
Project conclusion and impacts. This project successfully achieved the goal of developing an emotionally responsive electronic pad that enhances user interaction and companionships through the integration of vision, touch, voice, and light feedback. The development was structured into three main functional modules. The first is vision, touch, and voice module. The electronic pad can recognize user intentions and respond with appropriate emotional and physical feedback by integrating gesture recognition, touch sensors, and a natural language interaction system. The second is the obstacle avoidance module. Using cliff sensors and sonar detection, the pad can autonomously navigate around people and objects in a household environment, ensuring safe interaction. The third is light expression module. The emotional state of the pad, such as happiness, fear, or confusion, is visually conveyed through dynamic light color changes, enriching the pad's expressiveness. This project provides a versatile platform for advancing human-robot interaction technologies in smart home settings. Emotionally intelligent robotic pads show strong potential for application in elderly care, psychological companionship, and early childhood education.
First, the accuracy of visual recognition is limited in complex lighting conditions. The effectiveness of gesture recognition and obstacle avoidance may decrease. To address this, introducing more advanced deep learning modules, such as transformer architectures, can significantly enhance both the accuracy and robustness. Second, the robustness of speech recognition needs improvement. The existing speech recognition system may struggle to accurately recognize speech from different users, particularly those with different regional accents. Employing adaptive speech recognition technologies can improve the system's ability to handle different vocal features and dialects. Third, the current tactile feedback is limited. At this stage, tactile sensing is confined to basic trigger-based responses, lacking refined tactile perception capabilities. To improve this, incorporating multi-touch sensors or force-sensitive sensors can provide more detailed tactile interaction, enable richer and more responsive user experiences. Plus, the system lacks stability and real-time performance due to hardware single-threaded limitation and communication method of continuous transmission control.